This is a lecture on 4-4, the counting rules. The first counting rule is the fundamental counting rule. The number of ways that you have in your sample space, the number of possibilities in your sample space, depends on the number of choices of each event. So you're going to end up with K1 times K2 times K3 all the way down to however many things you're talking about. My first example is in the book. So the perfect illustration of the fundamental counting rule is through tree diagram. So we have few events. This is example 4-38. We have two events. One is a coin toss, and the second is a roll of a die. The question is, find a number of outcomes for the sequence of the two events. First, a coin is tossed, and then the die is rolled. So you know that a coin toss has exactly two outcomes, either heads or tails. The roll of a die has exactly 6 outcomes, 1 through 6 on the faces of the die. So what you end up with the fundamental counting rules, the number of outcomes, your sample space, the number in your sample space, has to be 2 times 6, which is a 12. The perfect illustration of this is through tree diagram. So you have either heads or tails on the coin, and then 1, 2, 3, 4, 5, 6 as your choices for the coin, for the die. 1, 2, 3, 4, 5, 6 your choices for the 1, 2, 3, 4, 5, 6 your choices for the die. So if I'll take one of these, just kind of illustrate. Let's say I get a heads and I get a 3. So this outcomes is heads and a 3 on the die. Count 6 and then 6 more, that's 12 outcomes. My next example is 438, and even though I can draw a tree diagram to illustrate it, it's going to get really messy because there's more outcomes to talk about. So in 439, a paint manufacturer wishes to manufacture several different kinds of paints. The categories include color. We have red, blue, white, black, green, brown, and yellow. I'm going to count them. Red 1, blue 2, white 3, black 4, green 5, brown 6, yellow 7. I have exactly 7 different colors to talk about. Type. It's either latex or oil, so there's 2 possibilities over there. Texture. Flat, semi-gloss, or high gloss. So texture. There's only 3 possibilities there. And use. It's either outdoor or indoor. So again, there's only 2 choices over there. I'm not going to draw a tree diagram for this type of situation. It's going to get too messy. The number of outcomes, of possible outcomes, can be determined by the fundamental counting rule. So 7 times 2 times 3 times 2. You're going to get 9 times 5, 45. 7 times 2 times 3 times 2, that's 7 times 2, that's 14, times 3 times 2, I need my calculator for that, it's 84. My next example. The first 4-41. The first year the state of Pennsylvania issued railroad memorial license plates, the plates had a picture of a steam engine followed by 4 digits. Assuming that the repetitions are allowed, how many railroad memorial plates could be issued? So what I have, I'm not going to draw a little train, but then you have 4 digits that follow. I'm going to stress out the fact that repetitions are allowed, and we are assuming that numbers like 0000 is also a possible license plate. We are using a counting rule to determine the number of different plates. If you only have 4 slots, there are 10 possibilities for slot number 1, meaning 0 through 9. Those are my digits. There are 10 possibilities for slot number 2, 10 for the third one, and 10 for the fourth one. The fundamental counting principle tells me that you need to multiply all of the choices. So you end up with 1 with 4 zeros. Oops, wrong place. 1,000 different plates. License plates. I'm going to move on to the next counting rule, and we have a factorial notation. The factorial is using a symbol of exclamation point. My first example is not in the book. It's 5 factorial, and what it does is you take the first number, you multiply it by the next lower integer, you multiply by the next one, until you hit a 1. So 5 factorial happens to be 120. Why is this useful? This is a number of different ways to arrange a certain number of objects. So my rules are, I'm going to go like this, factorial notation. If you have a number that has an exclamation next to it, what we mean is we take that number, subtract 1 from it, multiply, subtract 1 from it, multiply, all the way until you get to a 1. Few rules is 0 factorial is 1. We do use factorial symbol for probability, and sometimes we need to divide by a 0 factorial, which is a disaster if you're trying to divide by a 0. What we mean by a 0 factorial is how many different ways I can arrange nothing and there's exactly 1, as in do not do anything. So that's what the 0 factorial is for. So my next example is 4-42, lock codes. A person needs to make up a 4-digit combination to open the lock on the garage door. The person decides to use 4 different digits for the first 4 digits, 0 through 3. How many different combinations can be made? I'm going to read this one more time. A person needs to make up a 4-digit combination. I know 1, 2, 3, 4. The person decides to use 4 different digits. I'm going to search out the word different, meaning no repetitions. And he uses 0 through 4. 0, 1, 2, 0 through 3. So 0, 1, 2, 3 are possible digits. So I do have 4 choices, 4 places where I need to make a choice, and 4 choices for each. So I need to start with 4 because I'm choosing the first digit. I have either 1, 2, 3, or 4. That's where the 4 comes in. Now, the next one, if I already used a 1, I can use it again because it says different, no repetitions. So now I only have 3 choices. For the next one, if I've already chosen a 0 and a 1, then that leaves me with 2 choices. Now, if I've already chosen 3 digits, that leaves me with whatever's left. This is why multiplying by 1 doesn't actually change the number of outcomes. The fundamental principle of counting says that you do multiply through, but at the end of the day, this is just 4 factorial, which is 24. My next example, or my next formula, is permutations. The formula for permutations has to do with the factorial. The arrangement of n objects in a specific order using r objects at a time is called permutation of n objects, taking r objects at a time. And it is written exactly like this. So n objects taken r at a time. My first example. A radio talk show host can select 3 of 6 special guests for her program. The order of appearance of the guest is important. How many different ways can this be done? So, the most important part of permutations is order matters. I will still track back all of the formulas to the fundamental counting principle. I'm going to read the problem 4-44 one more time. A radio talk show host can select 3 of 6 special guests for her program. So what we have is 6 guests. We're selecting 3 of them. Selecting 3 and order matters. I have 3 time slots. I have 6 guests, so my first one needs to be, I need to choose one of those 6. So I have 6 different possibilities for choosing my first guest. Now, once that person has gone, I don't want to use that person again. So I now have 5 to choose from and 4 to choose from. The counting principle tells me that this is a multiplication. I end up with 120 different ways of selecting 3 people where order matters. The permutation formula is 6 is the big number, so your n is equal to 6. Your r is equal to 3 because you have 6 guests and you're selecting only 3 out of those 6. So you take 6 factorial divided by 6 minus 3 is 3 factorial. If you rewrite this out at the 6 factorial, you have 6 times 5 times 4 times, and then 3 to 1, meaning 3 factorial. So at any point you can stop and substitute this with factorial. Notice that the factorial on the top and on the bottom cancel out, and you do end up with 6 times 5 times 4, which is 120 different ways. Now there is a button on your calculator that will help you figure these factorials out a little bit faster, and I'll try to show this in the next video.